We next introduce an alternative method of similitude, which is known as dimensional analysis. Most books in fluid mechanics deal only with dimensional analysis as a method of similitude. We believe that this is a method which is less powerful and is more difficult to use. That's why we have kept it for the end. The first known application of a technique similar to the present-day dimensional analysis was made by J.B.J. Fourier of the Fourier analysis fame in 1822. But the technique was first formalized in 1914 by E. Buckingham. The procedure assumes that the variables that control the physics of a phenomena can be formed into dimensionless groups. We would give here a kind of a recipe for carrying out a dimensional analysis. The recipe is rather simple, but the results that are obtained need to be interpreted carefully. The principal steps involved in determining the non-dimensional groups, which are the pi numbers that we've introduced earlier, are a list all the physical variables or parameters involved in the problem. Say x1, x2, xn, a total of n quantities, of which one and only one is a dependent quantity, a dependent variable or a dependent parameter, typically a dependent parameter, the rest being independent variables or parameters. Take, for example, the case of a pump, a water pump, like we discussed earlier. The increase in pressure delta P is believed to depend on the diameter d of its impeller, the density rho of the fluid pump, the RPM n, and Q dot, the rate of volume pumped. So we can write delta P as a function of d, rho, n, Q dot. Here the value of n is 5. There are 5 parameters involved. One of them, delta P, we treat as dependent parameter, and the other 4 are independent parameters. Choose a system of dimensions. For most fluid mechanics problem, a system based on mass, length and time, MLT, is an appropriate system. Write the dimensions of all variables in the chosen system. Determine the minimum number R of the dimensions required to express these variables. For most problems in fluid mechanics, this number equals 3. That is, dimensions of all mass, length and time are needed. So for R variables, of which delta P is dependent and the other 4 are independent, we write the dimensions of that. For Q dot, the dimensions are L cube T raised to the power minus 1. For diameter, obviously, is length. Density is mass into L minus 3. For RPM, it is minus 1 in time. And for delta P, it is M L minus 1 T minus 3. A fundamental theorem known as Buckingham pi theorem states that the total number of non-dimensional groups of a parameter, which can be formed by combining the n physical parameters and variables of the problem, is equal to n minus r, where r is the number of primary dimensions required to express the dimensional formula of the n physical quantities. So we had 5 physical quantities, n is equal to 5 and r is equal to 3. So we can form 2 independent pi numbers out of these. Select a basic group of r independent variables or parameters. The selection is made such that all the dimensions involved in these r quantities and that non-dimensional groups cannot be formed from the products of the powers of those chosen variables. Let this be x1, x2, xr. In our example, let us choose D, rho and N as the basic groups. The dimension of length are contained in D and rho. The dimension of mass are contained in only rho, and the dimension of time are contained only in N. All 3 dimensions are represented, and we cannot form a non-dimensional group out of these parameters. It is now possible to form n minus r independent pi numbers out of these variables. Pi I is xi of the remaining variables, what we have not chosen as the fundamental parameters, into the first parameter raised to power a1, the second parameter raised to power a2, and so on. And the I varies from r plus 1 to n. We organize this in this table. We have chosen the basic group D, rho and N. The other parameters are delta P, which is dependent, and Q dot, which is independent. We write the dimensions of this basic group. L is the dimension of D. ML raised to minus 3 is the dimension of density. T raised to minus 1 is the dimension of the RPM. Similarly for delta P and Q dot. We form a non-dimensional parameter as D raised to power A, rho raised to power B, N raised to power C, and choose A, B, and C such that they match up with the dimensions of delta P and Q dot. So we form 2 pi numbers. The first, we look at what we have formed with dependent parameters delta P. The power A, B, and C are found to be minus 2, minus 1, and minus 2. So that delta P divided by rho n square d square is a pi number. And the other with the independent parameter Q dot, and the value of exponents are 0, minus 3, and minus 1. So that this comes out to Q dot divided by n d cube. This is for the independent parameter and this for the dependent pi number. So we can say delta P divided by rho n square d square, the pressure developed by a pump, which is usually expressed in terms of the head h of the liquid, such that delta P is equal to rho gh. Using this, our non-dimensional dependent parameter becomes gh by n square d square. Dependent parameter. And the independent parameter is Q dot divided by n d cube. So there is only one dependent parameter and one independent parameter. So we can get one graph. For a pump, if we plot the head coefficient CH against the flow coefficient CQ dot, we get one single curve at all RPMs. The deviation at higher speeds is largely due to cavitation that takes place at higher speeds. And the higher the speeds, the cavitation takes place earlier. And that's why there is a performance deterioration due to cavitation. These curves separate out only because a new phenomena is introduced. As long as cavitation was not taking place, the only relevant independent parameter was the flow coefficient, Q dot divided by NdQ. And so the head coefficient was a simple function of this, a line for all RPMs, independent of the RPM. Thank you.